If today you have pure solid or pure liquid, don't include them in your KEQ. To give you a quick example, how are you going to write this K? Many students, they are going to write PO2 raised to the third power. Solid, so should not be pressure, right? Should be concentration. ClO3 to the second power, KCl to the second power. This is actually incorrect. The main reason is because you can actually include in the pure liquid or pure solid in your equation. It means actually this one cannot be included. This one cannot be included. So the really correct way is that you should not write this, you should not write this. Your K should simply be a function of oxygen pressure to the third power. How about this one? The K should be what? Should I actually include in this term? You should not. Should I include in this term? Yes. This term? Yes. So the term you should include it should be either the gas or solution. So low things need to be included in your equation. But if it says L or if it says S, which represent your liquid and solid, those terms just cross it out. So you know this case should be PH2 to the second power, PO2 to the first power. And then the very important concept is the unit of KEQ. These things probably you won't be tested in your midterm, but this is something that I feel like many students will ask me. Because in the kinetics, the unit of rate constant tells you a lot of things, right? But for the equilibrium constant, it's different. Even though when you write out equilibrium equation, you always use concentration terms. It looks like for different chemical reactions, you're going to have different units. But in fact, when you become more knowledgeable, you'll realize even though here we use concentration term, scientists actually just use a term called the activity to do all this calculation. So what activity means is actually a ratio between the concentration that you can measure in your solution to a ideal solution. When people say ideal solution means it is a 1M solution. Because this things is always 1. So when you do the calculation, it has no effect because it's actually a relative value. The unit has been cancelled out. The KEQ is in fact unitless. When we do these things more seriously, we compare the concentration of your current situation to the standard condition. Even though the value is the same, meaning is different. The unit has been cancelled out. So the equilibrium constant K is unitless. But the rate constant K, the lowercase k, it has its own unit. And those units provide the information of reaction orders. One very, very important thing for this chapter is you will learn a thing called the small x approximation, which is actually the approximation can make your calculation much simpler. But not all the chemical reaction can use this approximation. There's actually a few requirements. And the requirements are either you have very big Kc or very small Kc. Okay, when I say very big Kc, if you have a Kc larger than 10 to the fourth, or you have a Kc that's so small, okay, smaller than 10 to the negative 4, then you can use a small x approximation. But the way you use it will be slightly different. You can always think about the equilibrium constant K is a ratio between your product over reactant, right? So if you have a Kc larger than 10 to the 4th, that means actually you have more product than your reactant by 10,000 folds. It's pretty much all product in your solution. Vice versa, if you have a Kc less than 10 to the negative 4, pretty much all the things in your solution, they're existing as a reactant. If today you have a very small k, which means your k is less than 10 to the negative 4, then you know there will be a very, very minor population of your reactant will be converted into your product. Under that condition, you know you can use small x approximation. If today my K is 10 to the 4th. Then I give you the concentration of my reactants. Once you mix them, what will happen? Yeah, they'll go to the product like crazy. So the net result is actually, even though I give you the initial concentration of my product, you can assume all of them become the product, and only very few of the product go back to your reactant. So that's the small x of your product going to go back to your reactant. So that's why in these two extreme cases, you can use small x approximation. If it's actually larger than 10 to the negative 4th or smaller than 10 to the 4th, you cannot use small x approximation. You will need to actually calculate things step by step. And eventually, this will be the equation you are going to use to solve the amount of change. There are 4 steps that you need to actually go through all the calculations. So step number 1 is to make sure whether you can use small x approximation. And the way you make the judgment is by looking at the equilibrium constant provided inside the questions. If it is larger than 10 to the 4th or smaller than 10 to the negative 4th, then the answer will be yes. If it is 10 to the 4th, then you know everything will be converted into the product first. Then the small x approximation is actually you're going back to your reactant. But if your Kc is less than 10 to the negative 4th, then you can just simply apply the small x approximation. Step number 2 is to create this so-called ice table. So the I stands for the initial condition, C stands for changes, E stands for equilibrium. And this is very useful because it actually follows your solved flow. When you read the questions, you know what is the initial condition. So you can actually write down the numbers on the questions. Then you know the reaction is going to occur, some changes is going to happen. And eventually you reach equilibrium, which you can actually use that information together with your equilibrium constant to calculate the final concentration. So once you do this, and then you can actually apply your small x approximation to solve for the x. And once you solve the concentration of each species, then you can actually go back and check out whether the things you have, you calculate the equilibrium constant, does actually agree with the equilibrium constant given in the question. If it does, then you are all set. Okay, you know you have done things properly. Okay, question number 1. When I2 initial concentration of 4.5, I did not type it, but it will be given in the question, okay? So for a reaction where the I2 in the gas form is going to go to 2I minus in the gas form, and it has the Kc like this. It tells you the initial concentration of your I2 gas is 0.45 m. Calculate the concentration of I minus at equilibrium. So we are going to go through this step by step. Step number 1, we want to determine whether we can use small x approximation. Can we use it? What is the criteria? You want to have Kc either larger than 10 to the 4th or Kc smaller than 10 to the negative 4th. So right now you know your K is 5.6 times 10 to the negative 12. Small x approximation. Okay, we can use it. The Kc is actually very, very small for these specific reactions, right? The major species in this reaction should be your reactant. You should start with assuming it only exists as reactant. What is your second step? The ice table, right? Okay, so in order to use your ice table, you want to actually write out your equation again, okay? I2 in the gas form is going to become 2I minus in the gas form. Then typically you do I, C, E. So what is the initial concentration of I2? 0.45, right? What is the initial concentration for I minus? It's not given, right? That means actually the reaction haven't started, okay? They give you the initial one. That means actually at the very initial stage, there's actually no product, okay? If it did not mention anything about the concentration of your product, just put 0 over there. So once you start the reaction, some change is going to happen. Your reactant is going to decrease. Your product is going to increase. So assuming there's actually X moles of your reactant has been disappeared. And those things will be converted into your product. If it's actually minus X for your reactant, what should I put on my product? Plus X. You want to pay attention to the coefficient though. There you go, 2X. Right? Because if you consume 1 mole of I2, you produce 2 mole of I minus. Therefore, you know, if I put negative X, because it's consumed, then going to form the product, and the concentration should be actually twice. So once you know that's the change you are going to have, and then once you reach equilibrium, then you know at the very end, there's how many reactants you are going to have. And then there will be that much product you are going to get. This is just you add up the initial and the change, and you're going to reach your equilibrium. Number 3 is you're going to solve for your X, right? From this equation, you know you can write your K is going to equals to I minus to the second power over your I2 concentration. What is the concentration of your I minus? At equilibrium. This is a KEQ, right? It means that is the final things you can put into the KEQ equation. What should you put in your I minus 2X? Don't forget raised to the second power. How about your denominator? That's right. Okay. So here is actually where you're going to apply the small x approximation. So because your x is going to be very, very small. So if you write out 0.45 minus x, you will be very, very close to 0.45. So you can actually make that assumption and then make the calculation a lot simpler. On the top will equal to just 4x squared. And then you know the Kc is going to equal to 5.6 times 10 to the negative 12. So you know your x squared is going to equal to, I'm going to move this one to the right and then move this one to the right. So what you're going to have is actually 0.45 times 5.6 times 10 to the negative 12 divided by 4. X is going to equal to the square root of this whole thing. So if you do the calculation, you can get a number of 7.9 times 10 to the negative 7. So that's how you calculate the concentration of X. So remember, it's X. It's not the concentration of your each species. Because you know for each species, the concentration equilibrium is this. Step number 4. You want to make sure the answer, that the X you solve is correct. The way you check it is actually, okay, if that is my small x, then I can actually use that to calculate my K, right? Because I know if this is correct, and then when I plug back into my equation, which is like 2 times 7.9 times 10 to the negative 7 raised to the second power, divided by 0.45 minus 7.9 times 10 to the negative 7. If I do this calculation, then I should get back a number that should agree with the equilibrium constant provided inside the question. So when you do these calculations, you'll find out the value is actually 5.6 times 10 to the negative 12, which is actually exactly the same as this guy. Then you know you have done everything properly. I2 concentration at equilibrium and the I minus concentration at equilibrium. Okay, this can be calculated from here, right? That is actually your I2, that is actually I minus. So this will be 0.45 minus 7.9 times 10 to the negative 7. Okay, the other one is actually 2 times 7.9 times 10 to the negative 7. A chemical reaction, 2NO plus Cl2, they are all in the gas form, that's going to produce 2NOCl. It tells you, okay, if today you have NO and Cl2, they have both initial concentration of 2M. You have Kc of this number. You want to calculate the concentration of this at equilibrium. So what's our first step? First step is always check whether you can just use small x approximation. So step number 1, can we use small x approximation? Yes, right, because it's larger than 10 to the 4th, right? Now the next thing is actually to judge Should I start with all reactant or all product? Product, right? Because your K is actually huge. So we know we should start with product. So what does this mean? Okay, you will see that very clear in the second step. 2NO plus Cl2, that give you 2NoCl. And the Kc is 6.25 times 10 to the 4. So in your questions, you have initial 2M of NO, 2M of Cl2. But you know, if you want to use small x approximation, we will assume everything become a product to start with. So when you write out your ICE, you know your I want to start with all the things converted to a product. So if that is the situation you have, okay, you want to convert it all into product, then you know how many products you are going to have. If you look at the coefficient carefully, 2, right? So you need 2 more of NO with 1 more of CO2 that can produce 2 more of NOCl, right? So right now you know you have 2 more of NO, 2 more of CO2. You should be able to see that, okay, in the initial, probably you're going to have 2 more of NOCl because the coefficient is actually here to here is actually 1-to-1 ratio, right? Another important thing you should see is that if you consume all your NO, you actually only need to consume 1 more of your Cl2. Therefore, in your initial condition, you should still have 1 more of Cl2 existing in your initial condition. This is actually a very essential concept you need to know. So after here, the same thing is going to happen. You know, you're going to start with your product side. A small x is going to move to your reactant side now. You're going to have something going to decrease in your product side, right? Sometimes people prefer to, okay, just put minus x here. If you consume x for your product, pay attention to your coefficient, okay? You're going to form x for your NO, but you only have 1/2 of the x for your Cl2. So you can definitely do this, no problem at all. But some people doesn't really like the concept that you have fractions in front of your x. So some people will write minus 2x, x, and plus 2x. This is fine too. When you reach equilibriums, you will know this will be 2x, this will be 1 plus x, this will be 2 minus 2x. Okay, and this will be the equilibrium concentration for your NO, Cl2, and NOCl. So for step 2, the most essential part is actually, can you actually write out this expression for each species? And once you have that, the next thing is actually solve for your x, right? We know our k is going to equals to MOCl squared, NO squared, Cl2 first power. MOCl we know is actually 2 minus 2x second power. NO is actually 2x second power. Cl is actually 1 plus x first power. So here is actually the part we are going to do the small x approximation. 2 minus 2x is going to be approximate as 2. So your numerator will be 2 to the second power. So this will be 2x squared. 1 plus x will be just simplified into 1. This whole thing needs to equals to 6.25 times 10 to the 4th power. This will be 4 over 4x squared equals to 6.25 times 10 to the 4th power. 4 and 4 cancels out. X squared is equals to 1 over 6.25 times 10 to the 4th power. Therefore, you know your x is equal to square root of this whole thing. That's going to give you a number of 4 times 10 to the negative 3rd. So once you get your x, you will be able to know the concentration of your NO is going to equals to 2x. Concentration of your Cl2 is going to equals to your 1 plus x. Concentration of your NOCl at equilibrium is going to equal to 2 minus 2x. So once you calculate all those things, use those numbers to back calculate the corresponding equilibrium constant. Okay. And it should agree with the equilibrium constant given in the questions.